Hello, and welcome to our 2026 Jacobs Teen Innovation Challenge project, Sheltergraph. Meet the team. My name is Soham, and the other member is Rishika. Now, here's the problem. Nepal is prone to earthquakes. Nepal has experienced over 1,000 earthquakes of magnitude 4 and above in just the last century. In 2015, a magnitude 7 earthquake rocked Nepal. However, some houses collapsed, but others did not. Why is this? Well, what determines a house collapsing is dependent on its material and its natural frequency. If the earthquake shock frequency and the natural frequency of the house match, the house is at a higher risk of collapse. If the earthquake shock frequency and the natural frequency of the house do not match, that house has a lesser risk of collapse. A majority of people did not get any timely warnings before the earthquake struck. We conducted a survey, and over 80% said they received no kind of warning before the Gorkha earthquake in 2015. This is very dangerous due to the lack of standardized building codes, which can cause life loss and a lot of property damage. We also ran across a technical problem. Instantaneous earthquake sensing is not feasible because waves from the earthquake travel right before the earthquake actually happens. This is why we shifted our focus to creating an app and method that helps determine if the building you are in will be safe during an earthquake. Here's where smartphones come in. We went to the Burj Khalifa in Dubai, and we went to the top 2 floors and measured the natural frequency using our phones. The resonant frequency of the Burj Khalifa is known to be 0.09 frequency hertz, and as you can see, using our phones, the data also reflects that outcome. Because the resonant frequency of a common building in Nepal is not publicly known, we used our phones along with a high-tech professional-grade sensor called the RS4D. And as you can see in this graph, the data from our smartphone and our RS4D are pretty close together. We then went to an old mud brick building and a new steel reinforced home. And according to this graph, the steel beam house has a sharp dominant peak at 8.7 Hz, while the old mud brick house has a dominant peak at 8.7 Hz. The old mud brick home signature shows higher damping, and the mud brick home is like a sponge, as in it has many peaks, high peaks, which makes it more susceptible to earthquakes, while the steam beam house is like a bell where it has one singular high peak, meaning at that frequency it's susceptible to earthquakes, but otherwise it should be totally fine. To extract our smartphone data, we used an application called FeeFox, where we made a custom building frequency measurement app in the interface. To extract our Raspberry Shake data, we use the Swarm interface where you can actually view data in real time using 4 different sensors, and you can actually extract the data and put it into formats like Excel. In order to create accurate measurements, sensors are taped directly to structural columns or rigid corners. Devices are secured under heavy weights, like bricks, to eliminate instrument slipping. We bang on the wall next to the instrument to excite the building's natural frequencies, and measurements are taken across multiple floors, which are usually the top 2 ones. Gemini was used to do the signal processing on data from smartphones and RS4D. Why does this matter so much to us? Both of our team members have family and friends in Nepal who are very deeply affected by earthquakes such as the 2015 Gorkha earthquake. These earthquakes cause a lot of life loss throughout Nepal and a lot of property damage. We are hoping that this system and app, which we are making to be affordable and reliable, can help reduce this unnecessary life loss. And we also hope to increase awareness of earthquake-induced loss and how we can create better buildings in the future to avoid such heavy loss. We're not going to stop here. We hope to interview larger groups of people to make sure our app is affordable and there when people need it. We hope to increase the number of samples in the cell phone to get better resolution in data so that the output is much more precise. We also hope to incorporate AI to help make the app more accessible to people who might not be able to read graphs. We also hope to survey buildings in Nepal to understand materials used and help Nepal use better materials, and we also hope to work with the government and universities in the US and college to make sure our app is able to be widely used. Here are citations, and thank you for listening.